An important but a fairly intuitive classifier used to categorize an outcome, or even in some cases to predict a continuous outcome, is k-nearest neighbor. The basic idea behind k-nearest neighbor is that a record is classified as belonging to a class 1 or class 0 based on the predominant class in k of its closest neighbors. The idea of closeness or similarity in this algorithm is coming from the Euclidean distance concept. So consider 2 points A and B. Let's say that point A is given by the coordinates x1, y1, and point B is given by coordinates x2, y2. The Euclidean distance between A and B is given as the square root of x1 minus x2 square plus y1 minus y2 square. And if we had a point with multi-dimensions, we would have the same analysis for each of the dimensions of points A and B. So we do the same thing in this algorithm, where we take a point and we calculate its nearest neighbor or its neighbors based on the distance of the features between these variables. And then we can come up with either 1, 2, 3, and thus the name k, because k is yet to be determined, as what would be the optimal choice in order to most accurately predict our relevant observation. A key question in this algorithm is, how is k determined? So this is a two-step process. In the first step, we partition our data into 3 sets. We call them training. Training is the set used to build the model. Typically, 50% of observations belong to the training set. Then validation. Validation set is what we will be trying to check how accurate our model is. And we let 30% of observations belong to the validation set. And finally, test. And roughly 20% of remaining observations go to the test set. So the way this algorithm works is, suppose this is our training set, and we have n observations. So we have n in our training set. The algorithm will look at each record. Suppose we have m records in the validation set. It looks at the first record in the validation set, finds the closest neighbor based on Euclidean distance among each of these n observations in the training set. Then once it identifies the closest neighbor, it looks at the class of that neighbor. Suppose that neighbor, the closest neighbor, belonged to class 1, then our validation observation is classified as class 1. If the neighbor belonged to class 0, the observation is classified as class 0. Then it does it for every single observation or m observations of the validation set. And then it records confusion matrix. Then it moves back to the first observation, looks at the 2 closest neighbors, and the 2 closest neighbors could be this neighbor and this neighbor. So then the algorithm will look at the class of these 2 predominantly close neighbors. Suppose both of them belong to class 1, then this record gets classified as class 1. And then it does it for the second record, and then all the way to all these m records. Then again, it starts back to the first record, then looks at 3 closest neighbors among all n, and then looks at the predominant class. So it keeps doing this. So in theory, the number of neighbors can be calculated ranging from k equals 1 all the way to k equals n, or the size of our training set. But often we put a restriction on how many k's to calculate. And depending on the data set, we might say that the k value ranges from 1 to 20. So the algorithm will now do this exercise 20 times for every single observation, and the limit finding 20 closest neighbors and ascribing the majority class of those 20 to each observation. So then we get a confusion matrix for the case of n equals 1, or sorry, k equals 1, k equals 2, all the way to k equals 20. And then we can see which of these k's minimized the error in our validation set, and then that is the optimal k. Once we choose that optimal k, let's say that k equals 8. We will then use 8 neighbors to categorize our test set observations. The error we get in the test set will then indicate what can we expect the error to be in real life if we were to try to use k or 8 different neighbors to classify a record in our new unseen data. So in the limit, if k equals 1, we are just looking at the closest observation and giving it that class. If k equals n, so we just look at the majority class and we classify the new record to belong to that majority class. Again, these two are not very interesting cases, but sometimes the algorithm may say that k equals 1 is the optimal solution. We never really let k equals n. Or sometimes it may actually find a more interesting k, like maybe 8 in this case, and then that's the k that we will go with. Now, one thing to keep in mind is that because we're calculating Euclidean distance, so for example, let's look at the observation 1 and observation 2. The distance between observations 1 and 2 would be, if you think of this as the x-axis and then this as the y-axis, a combination of x and y gives us this record completely. So for second case, we have x2 equals this and y2 equals 26. So this algorithm would essentially look at the distance being calculated as 49 minus 671 squared plus 38 minus 26 squared. And then we will calculate the distance between 1 and 3, 1 and 4, and so forth. Now notice one problem with this measure. Average balances have a fairly high magnitude. So if we were to square the distance, for example, square the distance of 49 and 2100, we will get a very large positive number. And that number might dominate the distance measure. So when we are doing the k-nearest neighbor algorithm, to avoid one variable driving the entire distance or similarity measure, what we do is we standardize every single variable. So we standardize or get the z-score. So instead of average balance, we'll be looking at the z-score of average balance. Instead of age, we look at the z-score of age. Where standardization essentially is looking at an observation, subtracting from it the mean, and then dividing from it the standard deviation of. Doing this will convert all these variables to follow standard deviation with mean 0 and variance 1, and they will predominantly lie between -3 to +3, because as we know that 99% of observations in a standard normal curve lie between 3 standard deviations of the mean. So now each of these variables will have the same scale, and we will not have the case with any one variable dominating the measure of distance. So once we have this neighbor, for example, if we want to classify this observation, the red triangle, and suppose the dark circles denote class 1 and the empty circles denote class 0. So if you were to go with one nearest neighbor, then the nearest neighbor to this observation is this observation number 2, and that belongs to the lone default class. So we say that this agent is essentially very likely to default on the lone. On the other hand, if our k was 3, then we now get these 3 as potentially close neighbors. Again, we'd have to use the Euclidean distance to specifically calculate the distances, but if suppose the neighbors of this red triangle or this observation were observations 2, 6, and 7. The majority class in these 3 is class 0, so we would say that this observation is now classified to belong to class 0. So again, the number of neighbors we choose would affect the way we classify this record. We can next see some examples of how we would do this k-nearest neighbor classification, and then how do we choose the optimal k based on our results in the validation set.